Hello, am I audible? So if I'm audible, can you please write in the chat or can someone just let me know? Okay, so welcome to week 8 of the NPTEL problem solving sessions for the course Advanced Power Electronics and Control, which is taught by Professor Avik Bhattacharya. My name is Soleh Khan and I'm a PhD student at IIT Delhi. So today is our final uh, session for the Monday sessions, and so in for the week 8, the course contents that were taught uh, included the following. We started with power quality, the problems and how to mitigate those problems. Then the topics included linear and nonlinear control in power electronics, and finally uh, there was some discussion on applications of power electronics and conclusion. So what I'll do in this last session, since I did not get a chance last week to discuss some of the lecture contents. So I will talk about some of the topics that were taught in last week, week 7. I will talk about space vector PWM and matrix converters. And then I'll take one of the topics for week 8 and then we'll move on to the problem solving sessions. So, uh, so in week 7, space vector was briefly introduced. So I'll just also talk about the principle of space vector and how we use it. And so space vector is basically used for uh, polyphase conversion, where we have three phase or more than three phase uh, voltages and currents. So for example, we have a simple two-level voltage source inverter here. And the concept of space vector comes actually from three-phase AC machines. So I hope you've all studied three-phase AC machines, but in basically what we have in such machines, we have a stator, which is a cylindrical stator, and we have three windings inside the stator, at least three windings, and these windings are distributed in space and they are 120 degrees apart. So when I say they are distributed in space 120 degrees apart, I mean that physically we have a cylindrical stator and the spherical portion or the circular portion, we have one winding, let's say horizontal, it has a horizontal configuration. The other winding will be spaced 120-degree apart from the first winding. And the third winding will be spaced another 120-degree apart from the second winding. It is a physical positioning of these windings. And so they are distributed in space. That is how where the space vector comes from, this term. And when we provide three-phase balanced currents to these windings, now these currents, they have a phase shift in time. So there are two things happening here. We have a distribution or a positioning of the windings in space, and then the currents, we have a phase shift which is in time. That means first the phase A current will reach its peak, then after 120 degrees, phase B will reach its peak, then after 120 degrees. So this is 120-degree in time. So after some time, the three phase will reach its peak. So because of this time and space distribution, what happens is that the currents, they produce magnetic fields, and the sum of the three magnetic fields that we of the three windings, it is actually a constant uh, magnetic field which rotates along the uh, along the stator. So it's a rotating magnetic field which with a constant amplitude. So that is where the space vector concept comes from. Now we can extend this space vector to voltages and currents, even though there is no actual uh, voltage vector in the space. We can have magnetic field vectors or electric field vectors, but we can imagine or we can assume a voltage and current vectors also. to because it makes the analysis and understanding easier. So that is what we are doing here. We are imagining or assuming that voltages are distributed in space as well. So for example, the horizontal line here is the voltage of the A phase. So along this line, if we have any voltage, then we can say that voltage in the A phase, it will be along this line. That 120-degree apart, that is the voltage V3 vector here, that will be the voltage along phase B. So that is 120-degree apart from the phase A. And then another 120-degree apart would be phase C. So this diagram that you see here, so what does it mean? So first of all, if we look at the circuit, we have three legs for three phases, A, B, and C. Uh, Let us make a convention that whenever the top switch in each leg is on, we call that state as P for that phase. So for example, if the top switch in leg A is on, we will call it P state for leg A. If the bottom one is on and top one is off, then we'll call it O state for leg A. So in this way, we can have a total of uh, 8 states, right? So each leg can have P or O. So we have three legs. So two options in the first leg times two option in the second leg times two options. We will have a total of 8 options. And then we can now come to the space vector diagram. So we start from the origin. So if all the bottom switches are on, then we are at the origin. So 000 is we are at the origin. Now, if any of the phase legs switches in the any of the legs is on, then we will move to the right or in the positive direction of that axis. For example, if A phase top switch is on and the others, the bottom switches are on. So we will move in the positive A phase direction one step. So basically we will go from this point to V1 vector. So P00 will be this vector, V1. It is in the uh, A phase direction. Now, similarly, we can have a B phase direction. So 0 or OPO will be vector 3 in the B phase direction. Similarly, OOP will be vector V5 in the C phase direction. Now, so what about the other vectors? Now you can see, let's say if we are at vector 3 OPO direction, OPO state. Now, if we turn on the leg A top switch as well, so that means we have to move in the positive A axis direction. So that means we will come here. So if you see, this is the horizontal direction, that is the A phase direction. So by turning on the top switch of leg A, we will move in the positive A phase direction. So we'll come to the voltage vector V2. So this is PPO. So similarly, you can see that from, let's say from V5, if we want to come to, let's say V4, then we turn on, we travel in the B phase direction, in the positive B phase direction. So we will turn on the B phase switch. So from OOP, we will go to OPP. So the second P is for the B phase. So by turning on the B phase switch, we will come to vector V4 from V5. So in this way, you can understand how all these positions are coming. And similarly, the PPP position, if you can see, so in any, for example, if we start from OOO, then we go to V1, that means we are going in the A phase direction. So we go to P0, POO, then we can go in the B phase direction. So by turning on the B phase top switch, we go PPO, and now we can again go in the C phase direction by turning on the C phase top switch. So we will go in this direction. So we will reach back to the origin. So that means when all the top switches are on, we are back to the origin. So this is how the space vector diagrams comes about. So we have, out of the 8 possible states, 6 are active vectors. So that means they will give us an actual voltage at the output, and the other 2 are zero vectors. So that means we don't get any resultant voltage at the output. And that gives us some flexibility, because we now have 2 zero vectors. So depending on which zero vector we use, we will get some pros and cons. So now, using the space vector concept from the uh, three-phase AC machines, if we so we so now in the three-phase machines we have 3 windings and we are giving three-phase currents. It makes a rotating magnetic field. Now we can think of it in the reverse direction as well. So if we want a rotating magnetic field, we can divide it in these uh, 3 currents that are spaced apart. So similarly, if we have a voltage reference that we want at the output, so we want a Vref voltage at the output, and then we can divide it into its equivalent 3-phase components. And based on that, we will turn on some switch and turn on some other switch uh, based on what reference vector we want. So, for example, if we have this reference vector and it is in sector 1, so we will use the nearest 3 possible uh, voltage vectors. So that is V1 voltage vector and V2 and V0. These 3 are the nearest vectors. And depending on how long we turn on V1 and how long we turn on V2, we can achieve our desired reference vector. And the rest of the time in the switching period, the rest of the time will be given to V0 vector. So for example, if we have Vref and we can divide it based on the uh, vector analysis from mathematics, we can divide it into V1, a weighted portion of V1 for some time Ta out of the full switching time Ts, we will turn on V1, and for some time Tb out of Ts, we will turn on V2. And this Ta and Tb we can calculate based on Vref and how much is the DC voltage, how much is the Vref, and just this vector analysis, you can find out how much should be Ta and Tb, and then uh, the rest of the time will be for the zero vector. And now we have now if we have these timings of uh, Ta, Tb, and V0, the question is, how do we switch? How do we switch from V0 to V1 to V2? So we have a full Ts time interval. How do we switch between these two to get optimum performance? So what is done in conventional space vector is that we have 7 subintervals in one switching uh, time interval. So first of all, the T0 time, that is for the zero vector, is divided into 2, and one is kept for the PPP state where the top 3 switches are on, and the rest of the time is kept for 0 stage when the bottom 3 switches are on. So this equal division between PPP and OO creates what we call conventional space vector. In sine PWM or sine PWM, we have a similar situation in terms of V1 time, V2 time, and V0 time, but the division between PPP and OO is different. In space vector, these are divided equally. So for half the T0 time, we will turn on PPP, and the other half we will turn on OOO. And then uh, further, we can divide these times so that we will get only uh, one switching at one instant. So for example, we will start from 00 time O to OO vector. Then we will turn on the switch of phase A, and then we'll turn on the switch of phase B, and then we'll turn on the switch of phase C. So only one switching is happening at a time, and then we'll turn off them one by one. And the timings are given here. So the first T0 time we will have for 1/4 of the full T0 time. Then we'll have 1/2 of the TA time because the other half will be at the end. So it will be symmetrical across the midpoint of this whole time. So this is for one for sector one. How do we switch between the different voltage vectors? So this is just an introduction to the space vector PWM, and uh, then we have different considerations and for harmonic analysis and for multi-level. How do we uh, switch between them, and how can we use carrier-based uh, reference and a carrier to get space vector PWM, and what is the maximum amount of voltage that we can get at the output. So all these considerations we can study in the based on the textbooks, and I think some of it was taught in the course as well. So now I'll come to matrix converter or direct matrix converter. So what we have in the direct matrix converter compared to the uh, other type of AC. So first of all, matrix converter is an AC to AC conversion, usually polyphase AC to polyphase AC. So that means we can have three-phase AC to three-phase AC, or more than three-phase at one side, and uh, more than three-phase at the output side as well. We can have three-phase to single-phase also, and uh, we can have any frequency at the input and any frequency at the output. So that is different from cycloconverters, where uh, we were limited in the output frequency. We could not uh, go beyond some output frequency. But for matrix converter, we can have any frequency at the input at the output. So this is how a direct uh, matrix converter looks like. So first of all, we have the three-phase input. Then we have a LC filter to filter out the harmonics in the currents. And then we have the matrix converter, and then we have a three-phase motor at the output. The matrix converter has three groups of switches. So first we have a group switch. So they are connected from at the input they are connected to the three different phases, and at the output they are connected together to a phase of the output. So this is one group, and then we have another group for B phase output and another group for C phase output. And total we have nine uh, switching elements, and we'll see what kind of switches these can be. And as we know, the switch can be on or off. So two options in each switch, and we have a total of nine switches. So that means we can get a total of 2 raised to the power 9. That is a 512 possible switching states. Right? I hope that is understood, because each switch can be on or off, and we find out the different permutations and or combinations, then we will get this many possible states. But in actual matrix converter, we don't use these many states. So because we have two constraints. The first constraint is that two switches from the same group cannot be on at the same time. So for example, if we have the A phase output group, two switches from this cannot be on at the same time. Why is that? Because if we turn on any two of these devices, or even so more than one device, if we turn on in each group, we will basically short the input side. For example, if you see the first and second switch, if we turn them both on, that means we are shorting VAB. So the VAB voltage, input voltage, will get short. So that means we will draw a huge current from the input, and the devices will get damaged, and so the converter will just get damaged. So that means that in each switch group, we cannot turn on more than one device. So So that means at the most we can turn on one device. So if the first device is on, if SAA is on, then we cannot turn on SBA and we cannot turn on SCA. So that is the first constraint. The second constraint is that one switch from each group has to be on. So the first constraint told us that at least one switch has to be on. Sorry, the first constraint told us that at most one switch has to be on. And the second constraint is telling us that at least one switch has to be on. Because we are assuming that we have an inductive load. For example, a motor is a type of an inductive load. So if no switch is on in a group, that means the uh, the A phase current at the output does not have any path to conduct. And if it's an inductive load, that will basically mean it will lead to high DIDT because of breaking the output current. It will lead to high DIDT, and we will get high voltages, and we can damage the devices or the machine. So based on these two constraints, what we get is that in each group, one and only one switch has to be on at a time. We cannot have less than one, so we cannot not have all the switches are off in a group, and we cannot have more than one switch on in a group. So then that means that we can have three options in each group. So in the first group, either the SAA is on, or SBA is on, or SCA is on. So only these three options we have. And then similarly, we'll have three options in the B group and three options in the C group. So we'll get a total of three, uh, three times three times three. That's 27 options in total. So 27 feasible states we have now in this kind of a converter. So now let's talk about what kind of a switch each of these devices will be. And it is written here bidirectional switch, but let's actually see in some detail how it will get. So, so what is the voltage that each switch has to block? Okay, so in order to see that, let's turn on SBA in the A phase group, and then we can see what voltage SAA has to block. If SBA is on, so uh, for SAA, which is the top switch, on one side we have the A phase, and now when SBA is on the other side we will get basically B phase. So the voltage that is blocked by SAA will be VA minus VB or VAB, the line voltage VAB. And as we know in the for three-phase AC voltages, the line voltage is also an AC voltage. So that means the switch SAA has to block bipolar voltages, positive as well as negative voltages. And similarly, you can see for uh, CA also, the voltage that will come across it will be CB or VBC basically. So all these devices, they have to block positive as well as negative voltage. They have to block the line voltage of the input that can be positive as well as negative. And similarly, the current, you can easily see that the current, uh, let's say for a motor, it can be positive and negative if it is regenerating. So if we want a bidirectional power flow, then the current IA can be positive as well as negative. So these devices, whichever device is on, has to allow positive as well as negative current flow. That means it has to allow current from input to output as well as output to input. So that means all these switches have to be bidirectional switches. They have to block positive as well as negative voltage, and they have to allow positive as well as negative currents. And the most popular configuration for this bidirectional switch is what is shown here. So it is a IGBT with an anti-parallel diode and connected to another IGBT and anti-parallel diode in common emitter configuration. It can also be a common collector configuration, but here it is shown a common emitter configuration. And in this way, the and it will block both positive as negative voltage. You can find that out, and the current can be conducted. So we'll start from an IGBT and then a diode, and in the other direction we'll start from the other IGBT and the other diode. So this is how the each of these switches will look like. And so based on which switch is on, we can get the output voltages. So for example, here it is shown the output A phase voltage. So depending on which switch is on in each of the uh, in the A phase group. So you see here that at each time only one of these switches will be on. So based on these lines, you will see that they will not overlap because, like we mentioned in the first two constraints, that only one and at most one switch has to be on. So exactly one switch has to be on in each uh, phase, in each switch group. So you can see that here. And then based on the input voltages, because all three voltages we get at each phase output, this is the how the phase output will look like. And the fundamental of this kind of a switch to voltage is shown here. And so based on uh, by switching appropriately, we get a lower voltage at the output. So in this case, the output has the same frequency as the input, but we can also change that. So we can get different frequencies at the output as well. So this was about some basic introduction to direct matrix converter. For indirect matrix converter, I will not talk about that, but we have one problem based on that, and we'll just see the circuits of the different indirect matrix converters there. So now I'll just come to the linear control, which was taught in week 8. And in the lectures, what you were taught was basically a state space approach and a theoretical approach. I'll um, give an example based on a boost converter, and we'll see how to model a boost converter. And so my what I'll talk about mainly is about the modeling aspect, because if I go into control aspect, it will take too long. So I'll mainly focus on the modeling aspect, and then the control we can do on based on different control techniques that we have. So in linear control, what we do is uh, we first model the uh, converter in the following steps. So we find the equations of the converter in different subintervals. So as we know, for example, here I'll talk about DC-DC converters. We can, in one switching state, we have different subintervals depending on which switch is on. So we first find out the different converter equations in each subinterval, and then we average over the full switching interval, and we use what we call a small or linear ripple approximation, as I'll talk about. And then we find an operating point. So because these equations, they will be nonlinear, but we want to use linear control techniques, which are much easier than nonlinear control techniques. So what we will do is we will find an operating point, and then we will linearize our equations uh, at that operating point. And so this is a very popular technique uh, for finding the linear to model a system in a linear fashion. So, and it is called perturbation and linearization based on an operating point. And then we can use the linear control techniques based on frequency analysis, the phase margin, gain margin, those techniques we can use on our linear model of the converter. So we start, so for example, here we have a boost converter, and it will have a D interval and a 1 minus D interval or a D prime interval. And this is how the converter looks like in, or the circuit looks like in each of these intervals. So in the first interval, the main switch is on. So the input voltage comes across the inductor, and the load is basically fed by the output capacitor. And in the D prime interval, uh, the main switch is off and the diode turns on, and we transfer energy from the inductor to the capacitor as well as the load. So, so this is how the inductor and capacitor voltage and current waveforms look like. So in the D interval, the voltage across the inductor is V in, and then in the D dash or D prime interval, it is V in minus V out. And since in a boost converter, we know that V out is greater than V in, so V in minus V out, we will get an overall negative voltage. And the inductor current, basically, we can find out using the inductor equation L didt is equal to VL. So when we get a positive voltage across the inductor, the current rises and then the current falls. And for the capacitor current and voltage, we can also see that in the D interval, the because we assume that the capacitor has a voltage which is equal to the output voltage, so the load will draw an output current, a constant output current, and that will be provided by the output capacitor. So the output capacitor current will be in the negative direction. So it will be feeding the load. So it will have a negative current. And then in the next interval, sub-interval, the current through the capacitor will be IL minus I load. And we also know that in the boost converter, the inductor current is greater than the output current. And we can actually find out exactly what the equation for the inductor average current is. But anyway, the point is that in the D prime interval, the capacitor current will be positive. So this kind of a current we will get. And based on the capacitor equation, C dV dt is equal to the capacitor current, we will get this kind of a capacitor voltage or an output voltage. And when the capacitor current is negative, the voltage will fall. And when the capacitor voltage current is positive, the voltage will rise. Now here we have the small ripple approximation. That means we are saying that the ripple in the inductor current and the capacitor voltages is small enough that we can approximate them by their average value. So the gray line that I have shown here, that is the average value of the inductor current and the capacitor voltage. And we will assume that the ripple is small enough that we can take the average value as equal to the instantaneous value. Obviously, here you will see that it is, I have exaggerated the ripple here, at least for the voltage. In practice, the voltage ripple will be much smaller in scale than I have shown here, and that is where the approximation will be valid. For the inductor current, actually, if the because the current ripple is linear, then our approximation will also be valid, that we will approximate the instantaneous inductor current as the average inductor current. So then we can find out the expressions for the inductor voltage and the capacitor current in each interval, which are given here based on the circuits. And in the next step, we do the averaging. So now that we have the expressions in the D interval and the D prime interval, we find the average inductor voltage, which will be the time or the D times the voltage in the D interval and D prime times the voltage in the D prime interval. And D prime is basically the fraction of time for which we have D subinterval. So for example, the whole time is, let's say, Ts, which is the switching frequency or the switching period. D will be the fraction of time for which we have D subinterval out of the full time. So d will be a fraction. And similarly, d dash will be 1 minus d. D prime will be 1 minus d because d plus d prime should be 1. That is the total time ts. And if we want to find the average voltage, so for some fraction we will get input voltage, and from some fraction we'll get input minus output voltage. And here I have used the small ripple approximation. So I have replaced VI and VO IL by their average value. So these dashed values are the average values, average over one switching interval. So because of the small ripple approximation, I can say that instead of Vi minus the the instantaneous output voltage, I will take the average output voltage, the average across one, because I can take that because the ripple is very small. And then I can write the equation like this. And then because I know that d prime is equal to 1 minus d, then I can simplify. I will get this equation, Vi minus d prime times Vo. And this is basically equal to L di dt because this is a inductor voltage. And so on an average, it will be given by this. Similarly, I can do a similar thing for the capacitor current. I'll replace the values by their average, by their switching period averages, and then I'll simplify, and this expression will be equal to C dV dt based on the capacitor equation. So these are the converter equations I get when I average over one switching period. So now I will do the linearization, or I will go to the perturb and linearize step. So what this means is that we will have an operating point. So for example, the D, we will have a capital D, capital V input. So we have an operating point with some duty and some input voltage, and then we will perturb it at this point. So this D hat and Vi hat will be very small compared to the capital values. So So we will basically stay at the output operating point, but we will allow small deviations across that output point, and we will assume that at that point the dynamics of the converter are linear. Because so basically it means that at a particular point, uh, if the input changes is very small, then we can approximate the system to be linear. And basically these the changes in the perturbation in duty and input will lead to some perturbation in the inductor current and the output voltage. And similarly, we'll have a DC operating point and then a small signal AC, because the amplitudes of these hat quantities are very small. And then we can substitute all this these expressions in the equations that we had found out. And once we substitute, then what we do is basically we remove the DC terms, because you can understand that, let's say if I substitute VI dash as capital VI plus VI hat here, so I will get VI capital VI in this expression, and I will remove the DC terms. So capital VI is a DC term. So I will remove the DC terms, and I will remove the second order terms. So Vi hat by itself is a first order AC term. But if it is multiplied by any other small signal AC term, it becomes a second order AC term. So that will make it non-linear system. So I will remove the second order AC terms because I assume that these uh, hat terms are very small. So if I multiply them by another very small quantity, the resultant will be even smaller. So you can imagine that if we have a quantity less than 1, that means 0 to 1, a decimal quantity. If I multiply it by another quantity which is between 0 and 1, the resultant will be smaller than the two individual quantities. So that is how I can approximate that the second order terms we can basically ignore those terms. So when I do this step, I will basically get these equations. So the uh, this is what I will get, and these are the state space equations of this system for small signal changes. And then based on these two equations, I can find out the transfer function of the system. So I can write these as a state space system, and then uh, you must have studied how to find the transfer function from a state space system, and I can find out the transfer function of the output voltage to the output voltage to the duty or small signal changes in the duty, and it will be basically this equation for the boost converter. For an ideal boost converter, this is the transfer function. The control to output, this is called the control to output. The control is the duty and the output is the output voltage. This is the control to output transfer function for a ideal boost converter. So it's a second order transfer function, and so then now we want to control this kind of a system. We will have a system like this where this GPD is our converter. So this transfer function that I've shown in the first expression is GVD. Then we sense this voltage, the output voltage. So then we have a transfer function for the sensor. So usually it's just a gain, a linear gain. It doesn't usually we we don't usually have any dynamics here. And then we get a scaled output. And then we have a reference voltage that we want to achieve at the output. The error between the reference and the sensed output is given to our controller. And this is the controller that has to be designed. And the controller will give us uh, some voltage or uh, some waveform. And then we will give it to a PWM generator. And this block will generate a PWM signal based on our control output. So that will give us a duty that will be given to the plant. So in this way, we get the full system. And based on this system, the loop gain, the closed loop transfer function, we can design the controller for our particular case, which I will not go into uh, right now, but you can study from different books. And I'll suggest Fundamentals of Power Electronics by Robert Erickson and Dragan Maximovich. So, in fact, the previous content that for the modeling I have taken from that book only. So, if you're interested in more how to design the controller, you can find out from that book. So, yes, so now we can come to the problem solving. So let's see. Okay, so before we begin, let's have the short break right now, and then we'll just uh, come to the problems. And so these problems are in general for the whole course, not specific to the eighth week. And mostly these are uh, conceptual problems and not numerical problems. We have a few numerical problems as well. So while we take the breaks, if you are interested, you can write the answer, what you think is the answer for this question in the chat. So we will begin in 5 minutes. So at 6:55, we will continue. So, okay, so let's have the break. Okay, so we can continue now. So the first problem is what is used for critical loads when temporary power failure can cause a great deal of inconvenience. And the options are SMPS, MPS, UPS, or CCB. So what is of concern here is only SMPS and UPS to us because the other things are not related to power electronics. So when we talk about SMPS or switched mode power supply, it is usually in comparison to a linear power supply. And both of these are AC to DC power supplies. Usually the AC that we get in our homes, 230 volt AC, uh, and or 110 volt, depending on where you are. And then we require very small voltages, like 10 volts, 12 volts, 20 volts for our laptops, computers, battery, phone chargers. And these supplies, there we have these two options, linear power supply and then switch mode power supply. And one configuration of a linear power supply I've shown here. So if we want a very small voltage at the output, we will first have a transformer. This transformer will be at 50 or 60 hertz at the supply frequency, and it will step down the voltage. And then we have a uncontrolled full bridge rectifier, diode rectifier. We will get a voltage which will be smoothed out by the capacitor, and depending on how precise, so we will want a particular voltage, and then we have the series regulator, and then we have a low pass filter. So the problem with the linear power supply is, first of all, we have a 50 or 60 hertz transformer, which will be larger in size compared to a higher frequency transformer. And then the series regulator is basically uh, whatever the voltage difference that we want at the output, and we will have some higher voltage at the input. The difference is basically lost as heat. In a, the difference is basically uh, dissipated as heat. So that means this kind of a system has high amount of loss as well, and that loss will actually lead to high heat sink, a large heat sink. And so the overall size of this kind of a linear power supply is large because of the transformer and the heat sink, as well as the efficiency of this kind of a system is less because of the power loss uh, in the series regulator. For a switched mode power supply, on the other hand, so this is one configuration. First, we have the diode-based rectifier, and so this is directly connected to the AC input. Then we have a flyback converter. So this is a flyback converter, and this transformer of the flyback is it will be switching at a higher frequency, much higher frequency than the transformer of the linear power supply. So that is why this kind of a supply will be much smaller in size. And it will not have as many losses as well, because the only losses will be the conduction and switching losses of all these things, which is much smaller than the losses in the linear power supply. So that's why we can get uh, above 90% efficiency of SFBS, whereas linear power supply, depending on what is the difference between the input and output voltage, it will be less efficient in the 50 to 70% or 80% maximum. So this is for a switch mode power supply. But as you can see, we will only get an output voltage once we have an input voltage. But the question was asking about uh, for crucial situations when the input supply is interrupted, or there's a temporary failure. In that case, the what we use is UPS, or uninterruptible power supply, and this is how this that kind of a system will look like. It just a basic diagram. This will usually have much more other configurations as well. So we have AC, and then we have a converter, AC to DC converter, then that is used to charge a battery. And in case of when the input supply is interrupted, then we get an AC supply from the battery, using a DC to AC converter. And usually we also have some bypass paths so that when the supply is there, we will directly take from the AC supply without going through the converters and the battery. So, but anyway, the answer to this first problem is UPS. The second question is about HVDC transmission lines, and it is asking in HVDC transmission lines, we have both stations operated as inverter, both as converter, one as converter, other as inverter, or it depends on the type of load. So I don't think we have covered this in the lectures as well as the summary session. So I'll just talk about HVDC. So first of all, just a basic question. Why do we use high voltage for power transmission? So can anybody answer in the chat, or can, if you want to unmute, you can answer. So it's a basic question. Why do you go for high voltage in power transmission? Yes, to limit the power loss in the transmission lines. Because for the same power, minimize V square R losses. Okay, so if we have high voltage, how will V square R losses get minimized? Because if we have high voltage, then V is high, so V square will be even higher, and V square by R will be higher than for a lower voltage. So it is actually the I square R losses that we want to minimize. So for a given power, so power is voltage times current. If we have a high voltage, then the current will be less. And that is why for so to transmit a power through a line which has a given resistance, we want to minimize the current so that our overall power loss, the I square R loss, will be minimized. The V square by R we cannot use in this kind of a system because uh, so V square by R you have to have the voltage across uh, across the whole resistance. But this transmission voltage is not across the entire resistance. It is between the different lines. So, so that is why uh, the actual power losses will be given by I square R, which where I is the current through the resistance. So that is why for power transmission, we want to minimize the current. So that is why we want to have high voltages, and that is why uh, when electricity first came about, that is why AC was preferred because we have the transformer which we can use to step up the voltage. It only works for AC voltages. That is when DC voltages and DC power uh, did basically it did we could not use DC power because it could not be transmitted because we did not have a transformer to step up a DC voltage. But now that we have power electronics, power electronic converters where we can convert or step up DC voltages as well, that is now we can use HVDC, high voltage DC transmission. And the advantages are that it can be more economical over long distances. So even though we will require now converters to convert from AC to high voltage DC, but because the conductor length, conductor size, and conductor, because we now have only, instead of three phase, we have only DC voltages or DC power, which is the conductor required will be less. We will not have any skin effect or frequency related effects. skin effect, proximity effect. We don't have active power, reactive power. It is only feeding active powers. And we also have advantages over asynchronous interconnection. That means, so for example, in some part of the world we have 50 hertz AC, in other parts we have 60 hertz. If we want to connect between them, that requires some extra equipment. But for DC transmission, we just have one conversion from one AC to DC, and then the same DC we can transmit, then just to convert to the other AC uh, configuration. So these are some of the advantages. The disadvantage is that we require converter systems uh, at this transmitter as well as the receiver side. And because of these extra converters, the reliability of the system is also less because now we have more parts, more switches. So any of them can fail. So the reliability of the overall system is less. So these are the two uh, popular transmission configurations. So we can have a monopole system. So we have a three-phase AC. Then we can have a transformer to step up or step down, or mostly step up. And then we have some kind of a AC to DC converter, usually a controlled SCR rectifier kind of a system. So then we get the DC. And so in a monopole system, we have only one line, one DC line. And then we have another converter at the receiver to convert from DC to again to AC, which will get three-phase AC at the output. So on the one side, we have a converter or a rectifier system. On the other side, we have an inverter system. And the ground is basically the return path for the monopole system. In a bipolar system, we have two converters from AC to DC. One converts to a positive line with respect to a ground, and another converts to a negative line with respect to ground. And then it is transmitted, and again we have two more converter systems to convert from DC to AC. So the point is, in HVDC transmission, we have uh, an AC to DC converter at one side and DC to AC inverter at the other side. So the answer to this question is that one station acts as a converter and the other as an inverter. So the third question is for high power applications, dash are used as static switches, whereas for low power applications, dash are used. And the options are basically SCRs and transistors or diodes as well. So which devices are used for high power applications and which devices are used for low power applications? So what do you think is the answer? Yes. So this we have studied in the first 2 weeks. So basically, thyristors are used for high power, low switching frequency applications, whereas transistors like IGBT, MOSFET, and BJT, they are used for low power applications but for high switching frequencies. So the answer to the third problem is SCRs are used for high power applications, whereas transistors like IGBT, MOSFET, usually these two in power electronics, they are used for low power applications. The next question is about the loss of a snubber circuit. The capacitance value is given, the supply voltage is given, and the switching frequency is given. So this is how a typical RC snubber looks like. We have a switch and we have an R series in series RC connected to in parallel to the whole switch. So R and C are in series to each other, and the whole RC network is connected in parallel to the switch, so that the DVDT is across the switch is controlled. So we don't get very high DVDT and high voltage overshoots. So now, if you want to find out the power loss due to this snubber circuit, that will just be the energy stored in the capacitor times the switching frequency. So that will be the power loss. Power loss is basically energy divided by time, and or we can use the energy times the switching frequency. So the energy in the capacitor will be given by half CV square. So we are given the capacitor voltage and the capacitor value. So we can find out the half CV square, and then the frequency, switching frequency is 10 kilohertz. So the power loss in the snapper is 133 watts. So the answer to the first problem is 133 watts. So the fifth problem is about again HVDC transmission, a bipolar HVDC transmission. So we have two 6 pulse converters used for HVDC transmission, and they are rated for 1000 megawatts plus minus 200 kilowatt. So basically, one 6 pulse converter provides the positive 200 kilowatt, and the other provides the negative 200 kilowatt. What is the DC transmission voltage? So, what do you think is the answer to this question? C. So someone is saying C, which is 500. So how do you get 500? So we have plus minus 200 kilowatt. Okay, so the first converter, basically the positive DC line terminal will be 200 kilovolt with respect to ground, and the negative DC line potential will be minus 200 kilovolt with respect to ground. So the overall DC transmission is between plus 200 kilovolt and minus 200 kilovolt. So it is 400 kilovolt in total. That is the uh, overall DC transmission voltage. So the answer is B, 400 kilovolt. So the sixth question is asking that which converter circuit employs a turn on and turn off when the voltage or current through the device is zero at the instant of switching. And the options are conventional converter, multi-level converter, matrix converter, or a resonant converter. Okay, so this is, we have not covered this in the course. Conventional converter it is not a particular kind of a converter. It's just, we can have different conventional converters. But the other three options, we have talked about multi-level converter. It can be multi-level in AC or DC, but multi-level does not have anything to do with the uh, zero voltage or zero current turn off or turn on. Multi-level converter will reduce the voltage across the device, but it will not make it zero. Matrix converter, again, we just talked about it, and it does not have this feature which we are talking about, that is zero voltage or current turn on, turn off. So the what is left is the resonant converter. So I'll just briefly talk about a resonant converter. So resonant converters, they basically use LC networks which have sinusoidally varying voltage and current across them. The LC, the inductor and capacitor, uh, they are resonating with each other first of all, and they have sinusoidally varying voltages and currents. And this resonant frequency is tuned to the switching frequency. So based on what our switching frequency is, we will have a particular resonant frequency. And the advantage of this kind of a system is that we will have the switch will be turned on or turned off at zero current or zero voltage, and that will lead to reduced switching losses. But the disadvantage of this kind of a converter is that we have to optimize this LC network to one particular switching frequency or one particular operating point. If on the other hand we have an application where our operating point varies a lot, so our output voltage varies a lot, then it is difficult to optimize the resonant, because you cannot change the value of an L and C once it is installed in a converter. It is not easy to change. You can have some other options, but it is not easy to do that. So that is why for applications where our operating point varies a lot. For example, in a motor drive application, where if we want to change the speed of the motor, we will change the voltage and frequency, and the current level will also change depending on the torque required. So in that case, the operating point is changing a lot. And in that case, it is difficult to optimize the resonant elements, the L and C values, for our wide range. That means we will get a zero voltage, or we will get the reduced switching loss at a particular operating point, but not at all operating points. So for example, here is a zero current switching buck converter. So if you uh, without this network, the SLC network, if you see this converter, it is a buck converter. And in the buck converter, we have replaced the switch with a switch with an LNC network as well. And what the waveforms of this kind of a converter are shown on the right side. So before the switch is on, when the switch is off, the voltage that is blocked by the switch comes across the capacitor C. And then when we turn on the switch, the current through the switch rises. So the IL is basically the current through the switch, because the inductor is in series with the switch. So the current through the switch and the inductor rises. It cannot rise instantaneously like in the normal buck converter. So it will rise slowly. And once it reaches the average of the output current, at that point, the system will start resonating. The LNC will start resonating. And we have to basically tune the LNC values in such a way that when we have to turn off the switch, at that point the current will go to zero. So so that we have to uh, ensure that when the current goes to zero, at that point we will turn off the switch. So that will lead to a zero current turn off, or a zero current switching of the uh, of this main switch, and that will lead to uh, negligible losses, turn off losses. So that is how these kind of resonant converters operate. So this is just one example for resonant converter. We have many resonant converters for DC to DC, even DC to AC. So the but the point is that in resonant converters we use resonating elements, LNC elements, so that the voltage or current of the switch becomes zero at the switching instant. So that will lead to reduced switching losses. So the answer to the sixth problem is a resonant converter. The seventh problem is about reverse recovery of a diode. So the reverse recovery time is given as 3 microseconds, and the rate of fall of the diode current is given as 30 ampere per microsecond. And we are asked to determine the storage charge. So, so this is how the waveforms will look like. So the diode current, when it turns off, instead of directly going to zero, it will continue in the negative direction to just remove the space charge. And after, it will reach a peak, and then it will go to zero. And this QRR will be the space charge that has to be removed. And this is what the question is asking about. So we are given the TRR time, the total reverse recovery time, and we are given the slope of the rate of the fall of the diode current. So the QRR charge will basically be the area of uh, this triangle. So that will be half of the reverse peak current, the maximum reverse current, times the TRR. And we can find the IRM using the DIDT. So we are not given the TA and TB time separately. So we will just assume that TRR is equal to TA, given that if we assume that TB is very small. So that actually depends on what kind of a diode it is. But because of the limited information given in the question, we will just assume that TRR is equal to TA. And based on that, we can find out the maximum current. So the maximum current is just the slope times TA, or in this case, TRR. So that we can find out that the slope is 30 ampere per microsecond, and then we have 3 microseconds. So that means the maximum reverse current is 90 amperes. And then using the 90 amperes and TRR value, we can find out that the stored charge is 135 microcoulomb. So the answer to this seventh problem is 135 microcoulomb. So the eighth problem is a triac is used in which of these applications? A chopper, speed control of induction machine, speed control of a universal motor, or none of the above. So can anybody guess the answer to this question? So I'll talk about, so the triac looks like this. It is basically two SCRs connected in reverse parallel with the gates attached. So it basically becomes a four quadrant switch. It has a controlled turn on. It will block both positive as well as negative voltage and allow bidirectional current flow as well. So this kind of a switch, which application is it used in? The options are chopper, speed control of induction machine, or speed control of universal motor. Okay, so this is how the speed control of the induction motor and universal motor looks like. So induction motor has different kind of speed control options. So one option I've shown here is the V by F control method. So we can have a three-phase supply at the input, or we can have the direct DC supply, and then we don't use uh, then we don't need to use uh, the rectifier. But let's say if we have a three-phase supply, then we will first rectify the voltage. We will get a DC voltage, and then we have a voltage source inverter. And the voltage source inverter, we can control the output voltage as well as the output frequency. So we can have a V by F control of the induction motor. And as you can see in this kind of a system, we don't require a triac. The rectifier stage we can do with just the diodes, because we can control the voltage using then the inverter stage. And in the inverter stage, we can use basically IGBTs with anti-parallel diodes, or MOSFETs with anti-parallel diodes. So in the induction motor speed control, we don't require a triac. But in a universal motor speed control, the universal motor basically works on AC as well as DC. So we have an AC input, and then based on so based on what voltage we require, we can use a triac, and we can control the triac because the voltage can be positive as well as negative. So that is why we have to use the triac, and the current can also be positive as well as negative. So basically, in a universal motor control, we can use triac. So the answer to this question is C, the speed control of a universal motor. So the ninth question is about indirect matrix converters, and which of these the different types of indirect matrix converters allows only unidirectional power flow. So the options are ultra sparse, sparse, or very sparse, or it can be all of the above. So can anybody answer the for this question? Which of these allows for only unidirectional power flow? Okay, so let's see the circuits. So first we have the indirect matrix converter. So this is the conventional indirect matrix converter. And then we on the right we have a sparse matrix converter. And the difference is you can see in the inverter stage there is no difference. In the first stage we are reducing one switch in each leg. One control switch in each leg we are reducing. So this is how we get a sparse matrix converter from the indirect matrix converter. And then we can have a very sparse matrix converter. And here, so for the sparse matrix converter, in each leg we have three switches and four diodes. But for the very sparse matrix converter, we are reducing the number of control switches. So from three to we went to two control switches, but the diodes we are increasing. So this has eight diodes in each leg. And the ultra sparse, again, we are reducing the number of switches. So it has only one control switch and three or four diodes. So this ultra sparse has the lowest number of switches. So now how can we find out the uh, whether it allows bidirectional power flow? So a simple way to do it is just to look at the DC current, the DC link current. So this portion, if it allows both positive as well as negative current, then it's a bidirectional converter. So obviously the load side is same for all and it allows bidirectional power flow. So we'll just see at the source side. So for the conventional or the basic indirect matrix converter, you can see that a positive current or a from source to load, we can have a current through one switch and then one diode. So this will be the positive current. And the negative current will be again through the other switch and the other diode. So the indirect matrix converter, it allows both positive as well as negative current. The sparse matrix converter, again, it has the same network. So it will allow both positive or from source to load from one switch, one diode, and the negative current as well. So here also from the bottom side, you can see the negative current. Uh, we can go through the diode, and the positive current, it will go through the diode and then the switch. For the very sparse as well, you can see it allows both positive as well as negative current because the from source to load, it will be through one diode and then through the switch and again through another diode. So I hope you can see this. Let's say for C phase, I go through the diode and then through the switch. If you can follow my mouse cursor through the switch and then through the top diode. The negative as well, we can go through one diode, through the switch and through another diode. So it allows both directions of current. But now finally for the ultra sparse matrix converter, if you see the DC link current, it will allow a current from source to load. So that will basically be from the switch, or you can see from the diode to the switch to another diode, but it will not allow a negative current because we only have a diode connected to each phase, so it will not allow the DC link current to be negative or to be from load to source. So that is why the ultra sparse matrix converter is a unidirectional converter. It will not allow bidirectional power flow. So the answer to this question is ultra sparse matrix converter. And finally, the last question is a transfer function approach is applicable to which of these systems? So only linear time invariant systems, or linear time invariant as well as time varying systems, and linear as well as nonlinear systems, or all systems. So what do you think is the answer? This is more of a control system question. So what do you think is the answer to this question? For a transfer function approach, can it be used for nonlinear systems or time varying systems, or is it general for all systems, or is it only specific to linear time invariant systems? So, okay, so one person is saying linear as well as non-linear system. So this is more of a control system question. I cannot uh, go into the details, but yes, we cannot use the transfer function approach for time varying systems or nonlinear systems. The transfer function approach is only so applicable to linear time invariant systems, LTI systems. So for nonlinear systems, we have to use other state space approach as is mentioned in the chat. But for transfer function approach is only applicable to linear time invariant system. So the answer to this question is A, linear time invariant system. So these were all the 10 problems that we had for today. So if you have any questions, you can ask. So this is the last session we will have. Then tomorrow there will be some. The session will be conducted by the other uh, scholars. So this is the last session that I will be conducting. So if you have any questions, you can ask now related to this week's content. So no questions if you. So I will be here for some 10-15 minutes. So if you anybody has questions, you can write in the chat as well as you can unmute and ask through the microphone. And if nobody has any question, they can uh, they can leave. So thank you all for joining. So however many sessions you could join, thank you all for joining. And again, these lectures have been uploaded on YouTube, and I will upload the final one as well, the problem solving sessions. And the slides are also available in the YouTube description as well as in the course portal. You will get the Excel sheet to all the YouTube links as well as the Google Drive link for the slides. So, so thank you as well for joining. So for the exams, so you will have to go through the course content, at least the slides of the course. You have to go through them because uh, the assignment questions, it will be similar to the assignment questions, but it will may not be exactly the assignment questions. So you have to understand the equations. I think the theoretical questions will be mostly from the slides of the course, but the numerical questions you have to know the expressions, the equations of the different converters, especially the rectifier sessions. And most of the questions, if I understand correctly, if you have the power electronics book by P.S. Bimra, so most of the numerical questions have been taken from that book. So you can look into that. I think the PDF of that book is also available, Power Electronics by P.S. Bimra. So that book, as well as the slides of the actual course, so that you can use for the final exams preparation. Okay. As for the exam, how many marks it will be, I am not uh, aware of that. I'm not with that team. I don't interact with the professors. So you can probably ask in the main course portal. So there you will get some answer to how many marks it will be. So in the main course there will be some discussion forum. There you can ask that. So because there will be some other TAs which are working with the course coordinator, and so they can answer you how many marks the exam will be.